Hi.
Hello.
Okay. Cool. Okay. All right. So, let's see. So, hopefully, you guys got the announcement that we'll be having a quiz today. Um, we'll have it at the end of class, but just to say something about that, what I do is, well, the quiz is on Canvas. It's going to be a PDF, and then you'll just go access it. You can print it if you want to, or you can just like write your answers on a piece of paper, and then you'll scan it in using some kind of, usually using your phone, unless you have like a regular paper scanner. Um, and then you'll upload a PDF to Canvas, and that's how you'll submit your answers. Okay. Um, but yeah, we'll get to that. I do have the instructions on Canvas as well. Hopefully you've done that kind of thing, like scanning in at this point. Okay, cool. So, oh, and then also I do ask you to turn on your cameras for the duration of the quiz, so that I can, keep an eye on you while you're doing that. Okay, so let's get started. Like I said in the announcement, we are a little bit behind, so I'm gonna try and like pick up the pace. If you have any, so I would request that if you have like philosophical type questions about linear algebra as a whole, just try to save those till the end of class so that we can, get through things a little bit faster. Um, but I need to pull this up on here. Okay. So I had one thing to say about last time. So we left off with, let's see, I can find it on here. Not there, here. This was what we were talking about right at the end of class last time, right? And I just wanted to say that the textbook, the way that they give the answers to this type of question is a little bit different. And just so that we're clear, like when you're doing your homework or something, it might look a little different. So in the textbook, or like on my math lab or my lab math, whatever, the way that the answer would look is basically you would take this part right here, how we've written it. So we wrote x1 and x2 in terms of x3. So your answer would be just this. You'd copy this down. So negative x3 minus 4, x2 equals x3 minus 1. And then you would write x3 is free, or a free variable, right? And that would be your answer. So just these things together, right? So you could write your answer this way, or you could write it the way that I did. I guess the textbook doesn't do this until like section 5, which is a little strange to me, but just so you know, you can do it either way. Okay? They both mean the same thing. Okay, so that's just a clarification real quick. Now, okay, oh crap, I need to pull up. That's not right. Here, there we go. Okay. So today we're going to be talking about section 1.3, which is about vector equations. So the first thing we need to do is talk about what is a vector, right? So 1.3. So what is a vector? For us, it's just going to be an n by 1 matrix. So it will look like a column, basically. So it will look like a matrix, oops, that's wrong, like this, but it only has one column, right? Okay, so this is how I will denote a vector in this class. So when I'm writing down vectors, I write this little like arrow, but it only has like one slash on it. So this denotes a vector. In the textbook, vectors are denoted with like boldface lowercase letters. So you'll see that that's a little bit different, but and if you see anything that like I type up, it will be that the same as the textbook. But when we're writing things, it's hard to like write a boldface character. So this is how we do it. Let me see. These entries in the vector, these are called components of the vector. Right. You could also just call them entries, but I'll probably use both, terms. So just so you're aware, do we handwrite the name of a matrix? Okay. So usually we use capital letters for matrices, right? And we'll just write those normally. So the standard letters that you use are A and B. You could use other capital letters. C, D, E, F, and so on. But we try to stick to A and B. Those are standard letters to use for matrices, and we can use other capital letters as well. Okay. Okay. So this is a vector. We also sometimes call this a column vector. So this is also known as a column vector. Right. Which is, just comes from the way that it looks. Okay. So we consider a vector with n components to be, let's see, vectors with n components to be elements of Rn. Okay. And so an element is really just like the basic object that makes up the space, right? So normally we might think of R2, so the Euclidean plane, as being made up of points, right? That's how we usually treat it. So it has a bunch of points. In this case, we are going to instead consider the basic objects to be vectors, right? Okay, so instead of just having points like this, so I've drawn some points on here. In this class, instead we'll consider this to be made up of vectors. And so we'll have for each of those points a vector reaching from the origin to that point, right? R2 is made up of vectors, right? Okay. Now, so the number of entries in a vector will tell you where, what space it's in. So for instance, this vector I've written down, U, is in R2 because it has 2 entries, right? And then a vector with, let's say we use V, so 1, 2, 3. This is a vector in R3 and so on, right? Okay. And just to be clear about this, so geometrically, like considering this picture right here, a vector v that has components, say v1 and v2 in R2. This is, you can think of this as an arrow based at the origin and pointing towards, pointing to the point that would be v1, v2, right? Okay. Okay, so we can add vectors together. When we add two vectors, say we have u, that is u1, u2 up to un, a vector in Rn, and we have another vector in Rn v, so v1, v2 up to vn. Adding them together means we just add the components together, okay? So what we do is we add components. So u plus v is going to be, first I'll write it this way so we can see them lined up right next to each other. v1, v2 up to vn. And we get a new vector whose first component is going to be u1 plus v1. And then the second component is u2 plus v2. And the nth component is un plus vn. Right? So we add two vectors together and we get another vector that is in that same space, Rn. Okay. And they definitely have to be from the same space in order to add them together. Otherwise, we won't have all of the components lining up next to each other, right? Okay. Now, we can add vectors geometrically. So we can picture what this looks like in R2. Vectors geometrically in R2. So, for example, say I have, trying to draw this nicely. We'll do two vectors, so u and v, and u will be the vector 1, 3, and v will be the vector 4, 1. And I can draw those on here. So 4, 1 would be this guy right here. That would be v. And then u is 1, 3. So this vector right here. Maybe I should use a different color. I'll use a different color for u. Okay. Great, like that. And basically what we can do is just place u and
Is this
v.
when you do tip to tail, or is that different?
Yeah, exactly.
Okay.
So yeah, u and v, so end to end.
High school physics is, I'm having flashbacks to high school kinematics.
Yeah, exactly. Yeah, so you do use vectors a lot in physics. And so, yeah, there is obviously that connection. Yeah. Well, if you never took physics, we'll still learn about vectors. You don't need that, knowledge in order to do this. So you can place u and v end to end. So you'll just start. So say I start with v here and I take my u and I put the end of it at the tip of v and then draw, u right there. And then that will tell me where this ends up, tells me where the vector u plus v will be. So it'll start at 0 and stretch to where the tip of that one is. And in order to just complete this picture, you can do it the other way as well. So you could start with u and then place v at the tip of u, and it will stretch to the same point, right? You'll get the same thing depending on, or it won't depend on which one you start with, right? And so this always forms a little parallelogram like you see here. So I think in the book they call this like a parallelogram something. Ruler, I forget. Something. Anyways, so you can do this geometrically, and sometimes it's nice to be able to visualize that, but we can check that when we do this, what we get is actually what we would get if we just compute it using, algebra like we did defined. So u plus v, we add the components, that should give us 5 and 4 as our two entries, and we can check that this thing that we've drawn ends up at 5, 4, right? So that point, right? So that green arrow that represents u plus v does actually end up being what we would compute, right? Okay, now, the other thing that we can do to vectors is we can scale them. So we can also scale, and this means that we multiply by a scalar c. So we'll start using this term scalar, and really this is just a constant, right? So scalar just means constant, i.e. a real number, right? Okay. So the reason it's called a scalar is because we think of it as like scaling vectors, right? Okay. And when we multiply by a scalar c, we just multiply each entry or each component by that scalar. So multiply each component by c. So c times u is going to be, maybe I'll move this down a little bit. This is going to be, so say our vector u has entries u1 up to un. We multiply each of those by c. So we get c u1, c u2, all the way up to c un. Okay. So for example, if we take our, so let's say we have a vector 2, 3, multiplying that by the scalar 2 would give us, we just double each of the entries, right? So this would be 4, 6, and negative u. In this case, we would just multiply by -1 each of the entries. We would get -2, -3. We could also do 1/2 u, and that would give us 1 and 3/2, and so on. You can multiply by any real number. Right? Okay. And then if we think about what this does geometrically, so we can again picture this geometrically. So starting with our vector 2, 3, let me move this over just a little bit. Yeah. Here, so over 2, up 3. Here's u, right? And then, so I'll label that here. When we multiply by 2, that stretches it to, let's see, 4, 6, right? So it would end up, I'll just go over it kind of. So this pink arrow is the scaled version of u, right? Okay. And then you can also picture the other ones. Like for instance, negative u flips it, flips u around in the other direction. So it would be right here. This would be negative u. Right? Okay. So one thing I wanted to point out is that the vector whose components are all 0 is called the 0 vector, right? Kind of makes sense. And it is denoted with a 0 with a vector symbol over it, right? And so this is just the vector whose entries are all 0, right? Okay, so 0 vector.
For scaling, there's no way, because you scaled negatively and it went into the opposite quadrant. There's no way you can scale to get into like the second or fourth quadrant, right?
No, you can't. So it's actually not only that, but you can't get off of this line through u, right? Any scaling will just fall on this line. So you can kind of move all the way along it, but you can't get anywhere off of it, if that makes sense. Okay. Right. And we'll talk a little bit more about that idea later. So, okay. So I hope everything has been clear so far. We're going to move on to linear combinations. And so this is going to be another definition. So a linear combination of vectors, right? So say we have a collection of vectors. So we're given vectors v1 up to vk, where k is just some natural number. And say these are vectors in Rn. And we also have a collection of scalars, the same numbers, so scalars c1 up to ck, right? So given these vectors and these scalars, the linear combination is going to be where we take the scalar c1 times the vector v1 plus the scalar c2 times the vector v2 and so on up to ck times vk, right? And just adding all of those up gives us the linear combination. So it's just taking all of our vectors, multiplying it by some scalar, and then adding them all together, right? And then these scalars are called weights. The scalars, I'll just say explicitly what they are. So the scalars C1 up to CK are called weights. Okay, so we have linear combination, and then we have this special name for the scalars involved in that. Okay, so just a quick example. This is an example of a linear combination. So we take this scalar 2 times this vector plus the scalar 1/2, well, 1/2 times this other vector. And then we can compute what this would be, right? So this would just be 4, 2, 6. So we multiply each entry by 2. For the second one, we multiply each entry by 1/2. We get 1, 5/2, and 2. And then we add those two things together. So we have 5. This would be 9/2 and 8. Okay. Okay, so that is what a linear combination is. Okay, so here I'm going to refer you to the handout. I'm going to try and do something fancy and just insert it here. Yeah, there we go. Okay, so here's the handout that I posted earlier, I think yesterday. And the first thing is this, this stuff in this box, the algebraic properties of Rn. These are things that you might take for granted, right? Like we're stating them, but if you actually, do some examples and work it out, they might seem kind of obvious, but it's good to just make note that all of these properties are true, right? So that we can add vectors in either order, or we can, add the zero vector to any vector and get that vector back, right? So all of these things. Okay. So these will come up later, right? But it's good to make note of them now. Now, referring to the second part, so I took this picture from example 4 in the textbook. Right, yeah, exactly. So you may have seen this already, but I think it's a really good visualization. Like it's a really nice way of thinking about linear combinations and what you can get out of linear combinations. So just to make it clear, because this kind of gets a little mucked up, V1 is -1, 1. So it is actually right here, right? And then V2 is 2, 1, and it's right here. And then that grid that you see is all of the like integer linear combinations that you could make, right? So you could do 2 times V2, and that'll get you to this point. 3 times V2 will get you to this point. If you add a copy of V1, so say V1 plus V2 will get you here, and so on, right? So just from looking at this, you can kind of see that you could actually get any point in R2, right? You could add some combination of those two vectors together to get you to any point, right? So, yeah, let me write that out. So, note that if you consider all possible linear combinations of V1 and V2, it will cover all of R2. Okay, cool. So this brings us to a notion that is called the span. Okay, so we have another definition. This is the span of a collection of vectors is, oh, okay, let's name them. So say we have a collection of vectors v1 up to vk. The span is the collection of all possible linear combinations of V1 to VK.
So it's almost like a power set.
It is not a, it's not like a power set, it's a set. And it's generally infinite, right? But I think unrelated to power sets. Okay, so did I finish this? Of all possible linear combinations, let's say, of these vectors, V1 up to VK. All right, so this is the notation that we use for this is capital S PAN, so span, and then we use the set bracket, the curly braces, to enclose the vectors that we're talking about the span of. So V1 up to VK, right? Okay. Now, okay, just to say this a different way, a vector, say, we'll call it B, is in the span of V1 up to VK if we can find some weights. So if there exist weights C1 up to CK such that we can write B as that linear combination, C1 times V1, oops, C2 times V2 up to CK, VK, like that. Okay. Okay. So let's look at an example. So first we'll use this example that we had up here from the textbook. So if we consider those two vectors, V1 and V2, let me copy them down right here. So example, we want to consider this span of V1 was -1, 1, and V2 was 2, 1. Let's see. Question. What's the difference in notation between K and N? So I'm using K because it's different than N because I don't want them to be the same, right? So we're already using N for the dimension of the space that we're talking about. So we're talking about Rn, vectors in Rn. So I just want to use something different than that. And K is a nice one to use. Does the span cover all of RK? No, not necessarily. And like I said, so the K doesn't necessarily refer to the dimension of the space or the dimension of the vectors that you're talking about. It does, sorry, I got distracted. So we'll actually talk about this, what the span can cover in just one second. So let me get through these two examples and then we'll talk about that. Okay, so we have the span of two vectors here. We noticed that we could get any of we could cover all of R2 basically with those two vectors. So that means that the span is just equal to R2, right? Oops. Okay, so that's the first example. Another example is the span of a single vector, right? We can talk about the span of just one vector. So here, this is the vector 1, 1 in R2. We can picture that, so we can draw it. Let's say this is 1, 1. So this is our vector. The span of this is So similar to what we were talking about earlier, it's going to be all of the vectors along this line, right? So actually, I'll use a different color to make this clear. So we could imagine it's basically just any constant multiple of this vector or scale of this vector. So we could move along this line, but we don't get anything that is off of the line, right? So in this case, the span of 1, 1 is the line through the origin and the point 1, 1. And there are many ways we could describe this line. We could actually write down the formula for it, but I'm just going to word it this way, right? And we can see what that looks like in the picture. Okay. Wait, so there are questions. Let's see. Then the span of still B are unrelated to what K is. If K is more than 1. So it wouldn't matter what K was. You can't possibly span Rn with less than n vectors, right? So there is a relationship there. Right, so what I was going to say is that I'll talk about this now. Okay, so what you can have, so we could think about sort of the different cases that you could have. So for instance, if we have the span of just a single vector, and it doesn't matter what space it's in, just a single vector, n-dimensional, whatever, this will always be a line so long as your vector is not equal to 0. If it's equal to 0, then you get nothing. You just get that one point at the origin, right? But if your vector is non-zero, then the span is always a line, has to be. Okay. If you get, so if you're considering the span of 2 vectors, say v and w, this could be a line or it could be a plane. The case in which you get a line is, that would be because they're either, let me write this out, either your vectors are collinear, meaning they lie on the same line. So v and w lie on the same line, or one of them is 0. Or that's what that would mean. Otherwise, you'll get a plane. So, right. And then if you take, let's say v, w, and u, so if you take 3 vectors, you could get a line, a plane, or a 3-dimensional space. Line, plane, or 3D space. Right? And then you can continue this on, right? Okay. Let's see. K denotes number of vectors. Yeah, exactly. It's just for like listing out the number of vectors. Okay. So does that help like visualize what's going on with the span? Is everybody okay with that? Okay, let's see how are we doing on time? Okay, so probably we will.
I have a quick question.
Yeah.
So these statements, does this only apply to R2? But wouldn't the span of a vector in R3 be a plane?
The span of a single vector in R3 will still not be a plane. So with a single, let me try and draw this nicely. Okay, so here's R3, we can think about it right like this. And if we have one vector, let's see, it looks like this. The span will still be the line going through it, right? So we could just imagine like extending it. So it'll be a line in R3.
Thank you.
Yeah, no problem. Does the matrix always have to have 2 or more entries? So vector, not matrix. Yeah, generally when we talk about vectors, we have at least 2 entries. I mean, you could call like this a vector, but it's a little bit strange too. Number line vector. Yeah, we don't usually talk about vectors in R, like when we just have one dimension. It's not really necessary to, right? So it's sort of like a degenerate case. And so we don't, yeah.